Hey, welcome back. Today we're going to break down the core building blocks of modern AI. We're peeling back the layers on the three big architectures that have, and this is no exaggeration, completely changed what machines are capable of.
So have you ever stopped and wondered, how does an AI actually see a cat in a picture? Or how does something like ChatGPT remember the start of your sentence to finish it so, perfectly? Well, the answer isn't just one thing. It's actually three really brilliant solutions that we are about to explore one by one.
All right, let's jump right in. This whole story really starts with the deep learning revolution. You can think of this as the engine that's powering pretty much all of today's most advanced AI, from self-driving cars trying to navigate our streets to the large language models that are writing code.
So what does deep even mean in deep learning? It's actually simpler than it sounds. It just means the neural network has a lot of layers, and each layer learns to recognize something new, building on what the layer before it figured out. So the first layer might just spot simple lines and edges, the next layer combines those into shapes, and by the time you get to the end, the network can recognize something really complex, like a person's face. It's this awesome hierarchy of understanding, going from the super simple to the really abstract.
Okay, so that brings us to our first major problem. How in the world do you teach a machine to see, to process visual information? And that is where our first specialized architecture comes in, the convolutional neural network, or CNN for short.
A CNN is basically purpose-built for grid-like data. And what's a perfect example of that? The pixels in an image, right? But the real magic, the secret sauce, is that it learns to spot visual features all by itself. We don't have to tell it what an edge or a curve looks like. It just figures it out by looking at thousands and thousands of examples. It's kind of like how our own brain's visual cortex works.
You can think of the whole process like a detective investigating a case. First up, you've got the convolution layers. This is like the detective scanning the crime scene for any and all clues, finding all the important edges, textures, and patterns. Next, the pooling layers. This is like summarizing the key evidence, keeping the important stuff and tossing out the irrelevant noise. And finally, the fully connected layer makes the final call based on all that evidence. Yep, that's a cat in the picture.
And for anyone who's ever written a line of code, it is just wild that these two simple-looking lines basically represent the powerful eyes of the entire network. Conv2D, that's the part finding all the patterns, and max pooling 2D, that's the part that hones in on what's most important. It's just such an elegant and incredibly powerful one-two punch.
So where is this stuff in the real world? Everywhere. It's in medical scans that can spot diseases way more accurately than a human can. It's in a self-driving car identifying a pedestrian. It's how your phone unlocks just by looking at you. Seriously, this isn't some far-off sci-fi concept. It's technology you're probably using every single day, and it's all powered by CNNs.
Okay, so seeing is one piece of the puzzle. But what about understanding things that happen in a sequence, where the order of events is everything? I'm talking about language, music, even financial data. For that kind of problem, you need a network that has a memory.
And that is the job of recurrent neural networks, or RNNs. They are designed specifically for this challenge. They do it by maintaining something called a hidden state, which is just a fancy way of saying it has a form of memory. So, as an RNN reads a sentence one word at a time, it keeps this running summary of everything it's seen so far. That context, that memory, is absolutely essential for understanding what the sentence actually means.
Now, the very first RNNs, they had a major problem. They had a terrible short-term memory. I mean, they'd forget the beginning of a long sentence by the time they reached the end. That's where these huge innovations like LSTMs, that stands for long short-term memory networks, came into play. They introduced these things called gates, which was a brilliant idea that lets the network actually decide what information is important to keep around and what it can safely forget. And that right there gave them the long-term memory they needed for truly complex stuff.
And this amazing ability to remember context is what powers services we use all the time, like Google Translate, where you have to understand the whole sentence, not just individual words. It's also the magic behind Siri and Alexa understanding what you're saying. And it's even used in systems that try to predict things like stock prices by looking for patterns over time.
But here's the thing. Even with better memory, RNNs still had a big bottleneck. They had to process everything one piece at a time, sequentially. That made them slow, and they still had trouble with really, really long-range connections in text. And then, in 2017, everything changed. Enter the transformer.
This whole revolution really kicked off with this one, now legendary, research paper, And its title, Attention is All You Need, pretty much says it all. This wasn't just a small improvement on what came before. No, this was a complete, fundamental shift in how we even thought about processing sequential data.
So, what's the big idea with transformers? Well, instead of reading step by step, a transformer looks at all of the data at the exact same time in parallel. And it uses this incredibly powerful mechanism called self-attention to figure out the relationships between all the different parts of the input simultaneously. This makes it ridiculously fast and way better at understanding the big picture.
And this, right here, is the aha moment. The difference is just profound. An RNN reads a sentence the way a person does, one word after another, in order. A transformer, on the other hand, it's like it reads the entire page in a single glance. It can instantly see how the very first word relates to the very last one and every other word in between, all at the same time.
So, how does it pull this off? Well, self-attention lets every single word look at every other word in the sentence to figure out which ones are most important for its own context. So in a sentence like, the animal didn't cross the street because it was too tired, attention is what helps the model know that it refers to the animal and not the street. But wait, if it's not reading in order, how does it know the sequence of the words? Ah, that's where positional encoding comes in. It's basically like adding a little digital tag to each word that says, hey, I'm word number 1, I'm word number 2, and so on.
The impact of this one architectural change has been absolutely staggering. I mean, it is the engine behind pretty much all modern AI breakthroughs. We're talking large language models like GPT-4, way better machine translation, and even new approaches to computer vision that are starting to give CNNs a run for their money.
Okay, let's take a breath and pull all of this together. We've just walked through 3 incredibly powerful, but very different architectures. The key thing to remember here is that each one is like a specialized tool in an AI developer's toolkit. And the real skill is knowing which tool to use for which job.
This chart really lays it out perfectly. You can think of it like this. A CNN is a master of space. It's brilliant at finding patterns in images. An RNN is a master of time. It's all about tracking context in a sequence. And a transformer? Well, a transformer is a master of relationships, weighing the importance of all the data points at once. Each one has its own unique superpower.
So after all that, you might be thinking, where do I go from here? And look, these concepts might seem pretty complex, but I promise you, they are absolutely learnable. There's a really clear path forward if you're curious and want to dive in deeper.
Something like this 10-week path shows a fantastic journey. You start with the absolute basics, the foundations of neural networks. Then, you methodically master each of these architectures one by one. It's a structured, totally achievable way to build a real deep understanding of how all this incredible technology actually works.
So there you have it. We've explored the fundamental building blocks of AI as we know it today. CNNs, RNNs, and now transformers have given machines these incredible new abilities to see, to remember, and to understand our world. The pieces are all on the table, so the only question left is, what gets built next?